I hope you will also enjoy it. Okay, so I offered to talk on multi-messenger astrophysics, but of course I will talk about things which I am working on, I am interested in, and I think I know good enough. You're welcome to ask questions. It's gonna be more of an experimentalist, data analyst point of view. On the second lecture, we are gonna have some demo on sky localization. I will also introduce you something new, which I hope will be fully funded fairly soon. It's called CIMA, Cyber Infrastructure for Multi-Messenger Astrophysics. It was not advertised in Europe yet, so this is my first time when I'm talking about it, but our US folks who we work with know about this, and I hope this will revolutionize how we do experimental MMA itself. So that's going to be the second lecture, but right now, okay. All right, what's going on? Either enter, page down. Oh, I know. Okay. All right. So it's definitely not going, not going, not going. I think this is usually the case. Yeah, I stop sharing. Okay, let's do that. And apologies, where is it? Here. Yeah, somehow. Okay. It did it not a long time ago. Okay, so what are we, should I start slideshow first? No, that's not gonna work. I start Zoom first and we go from there. Share screen. Actually, let's do that. I share the screen. And then this is my screen and maybe it's gonna be happier this way. Okay, and let's hope it's going. Yes, it's going. Awesome. So actually, there is a short booklet written by Imre Bartos and Marek Kowalski. Imre is from LIGO, Marek is from IceCube. Actually, Imre also works in IceCube. Titled Multi-Messenger Astronomy, which was published in 2017, right around when GW 1708-17 was discovered. So there is a first definition of multi-messenger astronomy. They like to say astronomy in there. Exploration of the universe through combining information from a multitude of cosmic messengers, electromagnetic radiation, gravitational waves, neutrinos, and cosmic rays. I will not be nice to cosmic rays here. There are some difficulties doing MMA with them. I will very briefly mention, if I remember, when we will talk about a search time window. I have my own definition, and I love to call it astrophysics because I am more of a physicist than an astronomer. So connecting different kinds of observations. You see, I'm very much an experimentalist of the same astrophysical event or system. So what do I mean here? Event or system. Okay, so some say gravitational waves were discovered back in the 1970s by Huss and Taylor. And imagine, you have probably heard about that, right? Did you? Good. Imagine if LIGO was so sensitive that we could actually detect those gravitational waves right now. It's still there, it's not merging, but emitting, right? Directly. It's not that sensitive. But we would have a multi-messenger observation because we see gravitational wave signal, and of course we would see the pulsar signal. Actually, RC waves off. Probably we wouldn't see it, but there are other ways. So that's the point. So that would be multi-messenger observation. And there are similar things which will come up like that. I won't mention probably Lisa once again, but when Lisa will run, we're going to have multitudes of observations of in spiral link systems and some corresponding electromagnetic signature. So that's what I mean on system. Now, there was the other thing I said, event, and from now on, we will talk about that because I work on LIGO. What does LIGO say? A transient, actually, well, in the CBC searches, we see transient, really just the last few cycles of a merger. So it's a transient event. So I'm going to call event, astrophysical event, a given source, let's say a compact binary, which is merging. Okay. All right. So what are we going to talk about? First, some history, preparations for detection. This is important because we made that one single detection so far. This is it with gravitational waves. I will talk about GW170817 plus means there are a lot of counterparts. I was only involved with the neutrino search, so I will just mention what was seen. Then the main points will be MMA observational approaches, how we are doing multi-messenger astrophysics, astronomy. What is in the MMA data, mostly from the GW point of view, but I will mention some other things as well. And then the main question is, if you see a candidate MMA event, which means you have gravitational wave messenger, because I work on that, so I'm going to have a GW point of view, plus another messenger, which are within your search window and overlapping in localization, both in distance and direction. Is it real? Is it real? This is the main question. How do you prove it is real? Or what do you say? How would you prove it? And I will mention some things about how we are doing that for certainly for the high energy neutrino search with the LIGO vendor data. So there's a paper from 2010. Not that Marka is not me. My husband also an astrophysicist at Columbia. So we worked together. He put together a paper back in 2010, which is open questions in GW astronomy. So I know a lot of young folks here. Many of these questions not answered yet. So if you're looking for a new project that you haven't thought of, and you don't want your own new ideas, you can go back and look there. There are a lot of things there which are interesting, but of course there are a lot of things which we learn, like speed of gravitational waves. We pretty much there, like, yeah, it's speed of light. Of course, there's some tiny bit of leeway. We haven't found anything related to GR. Maybe I'm not saying we didn't search enough, but we would need a very high SNR event to maybe see something, and so on. So of course, where we are really moving forward, mass spectrum and spin distribution of black holes. I don't know how much that was discussed, but this is totally exciting part of LIGO data. So I will not say much about supernovae, but of course, that's another interesting event. So not just CBC searches, a supernova can give a neutrino signature, and it can also give a gravitational wave signature. And of course, there was another question back then. You read it, and I just picked a couple here. What is the electromagnetic emission of binary neutron star coalescence? And this is what we really learned about since GW 170817. So if you love to read about the history, how it unfolded, this study, multi-messenger astrophysics within LIGO, it's more like a sociology article. How did we get there, that we made that first discovery? I wrote an article into the LIGO magazine because this was, and I'm saying it to the young folks here, the way MMA started without any detections first, right? We just had data, but we really started with preparation. It was a grassroots effort, okay? It started with the younger faculty and mostly postdocs, grad students, deciding that we are forming our own grassroots group with telecons. It was called the X3 group. And that's where these very early preparations were made for those first detections. So this started back in the early 2000s. So I mentioned the supernovae. So there is the supernova early warning system. LIGO joined it in 2000. We didn't even have data yet, but let's get those warnings so we would know about that. We are still waiting, of course. We joined GCN, the gamma ray coordinate network, which is providing the gamma ray localization data. Of course, GCN is no use to send out not just GRB data, but LIGO data, IceCube data, Antares data, and so on. Some of the astronomers respond to the events and put their own GCN. Another thing for MMA, which is important, is really connecting the data itself, which is coming from, for example, multiple gravitational wave detectors. We did not have data sharing agreements with Virgo until 2008 or so, but there was some agreement that if it comes, we would actually join in network data sharing. This was NDAS, this was network, how we would be pulled together the data between the two LIGO detectors and Virgo. So there were some early trials back in early 2000. So these preparations are incredibly important to make that first detection, because first you need to put together the data. So this is more like a recommendation to read. This is a paper from 2013, how gravitational wave observations can shape the gamma ray burst paradigm is the title. This was a review article, and most of it was right on many years ahead before first detection. And of course, we can expect gravitational waves from neutron star, and neutron star black hole systems, and also GRBs from these, and maybe from neutron star black hole as well. And there are the different frequency regimes where gravitational waves can be emitted, and of course, at the end, you can form a black hole, or maybe a hypermassive neutron star. So this picture is still there, and this is what the theoretical motivation behind, behind all these searches. I'm not gonna get more detailed, but read the article again, because I wanna talk about methodologies mostly. So GRB is still history. We did the first GRB triggered search back in 2003. So there was a GRB 030329. I'm not sure whether it's still the record holder. It may be. It was the most energetic GRB observed back then. There is a question there. Oh, really? GRB. GRB is gamma ray burst. So, you know, back in early 2000s, we already were expecting that short gamma ray bursts would come from binary neutron star systems merging. When the neutron star merges, actually, well, we can go up here. Do I have that? Maybe I had this beautiful. Ah, there it is. Neutron star merges, right? As you see here on the screen, I think this is going to come back. You can get all sorts of emission, and this jetted emission would be a gamma ray burst. It's beamed, okay, and pretty energetic. So the observation tools for these are gamma ray satellites, mostly Swift and Fermi, but there are other satellites, Integral, and so on. Okay. All right. So we also did a lot of triggered searches. So each time when a GRB was observed, and we learned it from GCNs, right? We got the information, we looked back in the LIGO data and run an analysis. I know Jonah was actually showing a lot of different kinds of data analysis techniques. Yesterday, there are two main types of searches. One is burst search, and the other is compact binary coalescence searches. So in the first one, there is no model. We just expect that there is a transient in gravitational waves, basically an excess power in the data stream somewhere. And these burst searches could be applied, for example, for counterpart to a long gamma ray burst, because we don't know what kind of gravitational wave emissions we can get from a long gamma ray burst, which are at the moment said longer than 2 seconds. And then there is the short type, which we know by now that they are coming from the compact binary systems. There was another interesting study on GRB 070201, and then we, of course, made the first observation. Another question, which we raised back in 2010, and actually we were already working on it, can gravitational wave detectors provide an early warning to other observations? This is incredibly interesting because we know that gravitational waves will reach us first, certainly earlier than the electromagnetic, yes. So so why do I expect electromagnetic, or sorry, gravitational waves reaching us first? So this is for the compact binary coalescence. So until the merger happened, we are not forming, let's say right now for the GRB, we are not forming that jet. So there is some reaction of the system that you form a jet. It is a matter of seconds difference. And of course, we give some way, and there are some cases that are precursors, so there are actually a bit more possibilities. So I'm not fully saying it exactly that we know it's reaching us first, we expect it's reaching us first. So, okay. So what else did we do? So I said early warning. So what someone does, we expected that beyond GRBs, there will be some optical counterparts. We didn't know what it was, what it would be. There was one paper only from 2004, which was written by somebody who left LIGO, Julian Silvestre, that yeah, he calculated that there could be some optical emissions, and maybe we should point a telescope into the direction where gravitational waves were observed. So, of course, we didn't have anything else but data stream coming. Virgo did not join us, so we only had 2 detectors, but we said, let's try. Why not? We need to practice. At one point, we are going to have 3 detectors. We are going to have a better detector, but let's try it. No, let's prepare. So we did not have agreements with other telescopes. So you do what you can. So you get to a telescope which you can visit, and one of them was MDM, where Columbia has a connection with, actually a part of it is Columbia owned. And then we also had access to SWOPE. I will tell you why SWOPE is interesting shortly. And we basically looked at the data. I'm not going to say fully real time, and certainly not automatically, but close enough. As the data was coming in from the 2 LIGO detector, we basically figured that the time difference between any triggers, between things which looked similar for 2 burst pipelines where we had seen excess power, and it was within 10 milliseconds, because that's the time of flight between the 2 detectors, the maximum time of flight. And we tried to do triangulation and find the time difference, and that gives you basically a circle in the sky. We got the galaxy catalog to that reach of 20, it wasn't even 20 megaparsec or 25 megaparsec. Yes, it was before S5, or maybe it was before it was 2007. I think it was S4. We could look for galaxies within LIGO's reach in the catalog, and basically point telescopes in there. So it was basically an exercise, but we wrote a paper on that. And that paper was like a proof of existence that this can be done fairly fast. And we basically got on in a tour of astronomers, at least in the US. Hey, help us. We are going to have in the last year of initial LIGO running in optical follow-up program. We tried this, but we are not astronomers. We want you to operate those telescopes. We want you to point those telescopes. This is what we tried, and we recruited order of 10 partners, And that was at the end of the initial LIGO era when we had 1/10 of the sensitivity than what we have right now. Remember, 1/10 of the sensitivity, this was pre-dimensioned by LIGO means we have 1,000 less event, right? So because the LIGO sensitivity, if you do a twofold increase in sensitivity, it's going to go by the cube. You have 8 times more event rate. Okay, so when advanced LIGO started, of course, we were expecting to see things. Yes. So the only optical counterpart which we have seen and observed was GW170817. We don't think it was lensed. There is gravitational wave lensing as a very, very interesting study within LIGO and a couple of papers, but it's more on the GW side. There could be some lensing, obviously. Yeah, but we have one event so far, if you're asking about the optical. Oh, yeah. It's electromagnetic, especially in the optical, it's delayed. We will talk about GW170817 soon, and you will see some delay. But of course, it would be lovely to see as early as possible. Okay. Moving on, there was a key ingredient. And I know there are lots of theorists who were interested in what is the optical counterpart, but I can tell you what really helped us to convince the astronomers beyond the 10. So it became 80 when we started to run the optical follow-up program. After LIGO restarted back in 2015. And this was a key paper by Brian Metzger. This is showing a binary neutron star event. You can see the jet forming here. These are the neutron star. You form a black hole. You can get GRBs. You can get afterglows. But you know that's coming fast. This is seconds. Yes, nobody. If Swift is not pointing into that direction, it may not get it. Okay. So, but here is something which is called kilonova. And I don't know how much was mentioned, but the point here about the kilonova is that according to Brian's calculations, it's delayed a lot. You can actually see the emission in the IR up to a week or 2. Now, that's plenty of time for an astronomer. That's plenty of time. And this was really a key ingredient for the electromagnetic follow-up program to really take hold and convince astronomers to join us. So there was a bit of anonymity from the astronomers, by the way, because US spent, NSF, National Science Foundation, spent a lot of money on building LIGO. And astronomers, some notable ones as well, would have loved to spend that money differently. Maybe that was not the only thing, but I don't think that they were not believing that gravitational waves exist. I think everybody believed it. They may not believe that the money spent on building that detector will result in a working detector which makes detections. Yes. Neutrino? Yes, you can have. I will mention a short time, in a short time. Okay, so particle messengers, and this is where I bring up supernova. Okay, and actually this was SN9 in 1987A was a multi-messenger event. It was observed, of course, in light as well by astronomers, and in neutrinos, you probably heard of that, order of 19 neutrinos observed between Kamiokone and IMB itself. And of course, the neutrino data analysts went back to look at that data because 50 kiloparsec is close. It's as we haven't had. This was a naked eye supernova, by the way. It wasn't in our galaxy, but was close enough. 50 kiloparsec is close enough. So, okay. So SNEWS was established. So all the neutrino detectors are working together now to join and send triggers when they see something into a common network. And if it's seen by many of them, then it's a real event. But why I am not so excited about neutrino analysis. I mean, if it happens, it would be big, but we have to wait for that galactic event. On the GW side, okay? So that, of course, on the neutrino side, it's not like we are gonna see things to many megaparsec either. So yeah, so we are not likely to observe a gravitational wave from our own, even from our own galactic supernova with the current LIGO sensitivity. The expected, the most accepted models say we have around the order of 2 kiloparsec reach, which is basically a fraction of our galaxies. So of course, also when that happens, we're gonna have a neutrino signal, a big one, huge, definitely. We can always go back and analyze the LIGO data. But in terms of what LIGO, Virgo, and COGRA can do, I mean, this waiting for that one in every 30 years or maybe even 100 years event is not easy, right? And you know, we are not always running. Should we be running at least one of the detectors all the time and do a schedule of the upgrades like that? At the moment, we are not doing that. I'm sure this may not make the supernova enthusiasts that happy, but at the moment, we are really trusting that the third generation detector will do the work unless we get lucky. Nonetheless, there is a tremendous effort to analyze the gravitational wave data for supernova gravitational wave signals. So I'm sure it will pay off when that event happens. Okay, let's go to high energy neutrinos. I am actually working with IceCube as well, and I'm running the GWN search. So IceCube is a detector at the South Pole. Yeah, sure. Oh, Andrew, you can go ahead with your question.
Oh, sure. So for supernova gravitational wave observations, are there models for waveforms, or would it just be a burst search?
There are models for waveforms. I'm not sure I trust them so much. There is a huge variation. In my opinion, there are certain aspects of most waveforms in the time frequency plane that look very similar. And I think the most promising, and I don't think it's just my opinion, it's mostly, it's an opinion by many of those who are doing the work, that what can bring us breakthrough would be a machine learning algorithm which are looking for those specific signatures. So this is not just the around 1000 Hertz signature, but of course the signature has a given time dependence. There's also a lower frequency portion of the signal or the expected signal itself. So that would be one way to do that. There are waveforms. It was a long. I don't remember whether 3D modeling resulted us a good enough waveform. So I don't remember. I haven't been following that part. Okay. So high energy neutrinos. So back in 2006, we had Chad Finley from IceCube, who used to be actually a Columbia graduate student. He went to postdoc on IceCube visiting us, and we came up with the idea, let's do this search, because both gravitational wave detectors and the neutrino, high energy neutrino detectors look at the sky nearly all the time. Well, IceCube definitely does. We sometimes turn off for years, but when we do look at the sky, it's in every direction and all the time for a long time. And we can easily combine the data, and whatever the sources are, which can generate this joint coincidence, it actually can be proven fairly well that it's a significant detection if we find such an event. So we did a lot of development with a larger GWN team. We had a couple of theories. We worked on what would be the time window. I will mention that in a short time. And what kind of source model is there. The compact binary coalescence is a source model. So we can have high energy neutrinos from a BNS event. Most likely related to the formation of jets. So beaming does matter, and then we would have to have the right type of system which points towards us, good enough towards us. So we haven't seen anything yet, but there are lots of results on upper limits, and we are also we are doing this in near real time, and we mentioned quite a bit about that. So let's look at GW170817. So we know about multi-messenger astronomy with gravitational waves from one event. It really is. And we wouldn't be here if we were not lucky on that day and the LIGO detectors were not running. Even if one of them wasn't running, it would have been, I would say, nearly impossible. And that nearly happened. So when the data came in, you see the top one, it's Hanford. You see the chirp here in the time frequency plane. And that was very clear. This gave actually an alert to all those who received the alert running around with your phone. And you didn't believe, oh God, we do have real, I mean, this was visible, okay? You run, this is called the Omega scan, you run it and it's there, it's a chirp and it's there. So Virgo did not really have anything, and what Livingston had wasn't this. I don't know, didn't Jonah mention this? Okay, so you know what was there. We had a huge glitch there, but the signal is there, right? So we had to get rid of that and combine, and there we go. I meant to say we did have a joint localization, but okay, we are gonna get to that slide in a second. We also had an alert coming through GCN from Fermi 1.7 seconds after our merger time. And it wasn't only Fermi which had seen the event, Integral had also seen that. So that's totally amazing. We did have, we knew it right away. This is it. We got it. It's like hitting the jackpot. Okay, and there is the localization. So of course, we had the LIGO. This was two bananas, not a circle in the sky. We can talk about that, by the way, right? I work quite a bit on timing itself and how these are recovered. And this was the Fermi localization. So it was a weak Fermi band, okay? What really was telling us a lot that it was 1.7 seconds after the gravitational wave trigger. So that was the excitement here. So was this a special event? Um, I think so, but not because of what we learned from it since then. I think it was special because it was so close. At the moment, it's hard to tell, right? For one event, it's very difficult to say and do statistics. So I could be totally wrong. Small number statistics is always difficult. So it's my gut feeling, and that gut feeling is coming mostly from GRV observations. So we did not know, of course, that this event is disclosed and would not have known based on Fermi observations only, okay? And Fermi, of course, is seeing events similar like this in fairly good numbers, but probably not as great that we can expect another one this close. But I hope I will be wrong, okay, on this. I don't know. I think the specialness was its closeness, okay? So we did have the localization from the joint localization from LIGO Virgo, and of course coincided with Fermi, and then astronomers did what we did back then. They were not expecting such a close by event. So actually we did give a distance as well. So you could just pull out your galaxy catalog. It's pretty much complete. And you could just actually rank your galaxies. Some of the astronomers were actually ready with that. What would be the right kind of ranking for that? So they were looking, and those who really pulled out instead of just, I try to tile, because that's kind of position still big, right, for regular telescopes. So you really have to do some other things. You can do the hard work, start tiling and brute force, but those were winning who actually pulled out the catalog and really did the ranking and looked, and then they found the right galaxy where this signal came from. And it wasn't observed only in optical, although that was probably the biggest, search. It was also observed, and that was the first thing. So after that, everybody else knew where to point. So it was observed by X-ray telescope. It was observed, for example, by Chandra, also in radio over a week afterwards, and so on. Okay, so this is a light curve. You can see as it's fading, it started actually pretty blue. We will talk a little bit about that, but you can see this is in microns. So you have a lot of infrared emission there, and I don't know which day are we. It should be showing the days. Yeah, so it's 6 days. So you see it's still in infrared for a long time. So, yeah. Okay. This is a slide which I love to show. You have seen this slide? Brian Metzger, Brian Metzger is the theorist. He's at Columbia. I did not say that. When this event was observed, of course, he heard the rumors, and as soon as they had the optical observations, he pulled out his paper from 2010. That was the very first paper on kilonova emission and the discussion of how long you can see an optical counterpart, and this is the fit. It's beautiful. So he loved to show this slide right at the beginning when we made the announcement. So this. Sorry, the black line, it's just the power law line of how it changes with time. So that's a fit. I don't know whether it came from his model. You can look at the paper. Yeah. I don't know. I don't know. I don't know. For me, it was just beautiful already that this is going there. I don't know. How many days that? 10. Yes, so some of the infrared gets built up at the later time. I will show a little movie if it's there. I think it's in my slide. And of course, it started out as blue. You probably seen that on the spectrum and the way it changed with time. So there was a blue part which was closer to the axis, most likely. And from the fact that we had seen blue and red at the same time, there's enough assumption that we are seeing this kilonova off axis a little bit, but not too bad. Of course, we know it's not too bad because the GRB came, but still off axis. Oh, yes. So why do you see all that infrared? So when that neutron star, those two neutron stars merge, a lot of neutrons are emitted, and you start, and they are pretty hot ejector, right? And they start to do their work in nuclear physics. So what you have here is Z versus N, the neutron, the atomic number, and the N as well. And you can see that you're forming larger and larger nuclei. And then they, of course, go and find the stability itself. But there is a lot of optical emission in the infrared when that is happening. And that's where Brian's model for kilonova came from. Oops, I went and that was not, I pushed the wrong button, guys. Apologies. We are here. Yes. Here. Okay, I'm going to the wrong direction. Yeah. Here. There is a time there, so you will have the movie, and I don't remember because it was a long time ago. I think if you look at the T there is a speed up somewhere, but maybe not. Maybe it goes that fast. It's all about rates, right? Because you're forming radioactive nuclei, and some of them, decay very quickly. Some decay very slowly. So certainly those rates are there. There could be some sudden burst there because some actually decay incredibly fast, but I don't know. There could be also speed up on the movie. I don't know which effect is here. Okay, and this is again right around the announcement. Of course, we were working together that the optical astronomers will put out their paper right after we put our paper. And this is one of those. And it's again a spectroscopy of the kilonova in the infrared and compared to Brian's model. So it's lanthanide and actinide emission, heavy element emission. Okay, so there were X-ray observations as well. It came a few days later. You can see that mostly done by Chandra, two different teams, same detector, and it was there. It was an X-ray detection of the same event, afterglow. So how can you explain the event itself? So there were two possibilities to think of. One is an on-axis weak short gamma ray burst because we know that the GRB was weak. And the other was slightly off axis, and which means that is the eye over there, and we are viewing the event from slightly off axis. So we have a little bit delayed X-ray and then radio emission as well. And we do have still a observation of a GRB, which is somewhat weak. So probably the second one is the one which is working. There are several papers on this. I think there is getting there to be a consensus, but people still go back and say different things. And it's still, actually, it's not just that. I would say the most, for me, okay, and because I did not work on the extra data, but what is the most convincing for me is coming from the kilonova observation of seeing both the blue and the red one. But I am sure there is another argument on the X-ray side. There's also the radio. It came a bit more than a week later, the observation with JVLA. Again, there are other papers showing that. And then this is Brian's summary slide, and which shows everything what was seen. And I'm gonna go and move on what was not seen, what we searched for. So this is going towards the work. So we looked at both Antares and IceCube data, and Auger, which is a cosmic ray detector. Of course, it's very high energies than the high energy neutrino detectors can have some indications of neutrino as well. So they also joined the effort, and this is the result. We did not have any neutrino coincident, spatially coincident with the localization. So we established an upper limit, and where we are hopeful that this may happen is that the models, if predict that if the BNS is even at 4 degrees, we may be able to see something at 8 degrees with IceCube Gen 2. We probably would see it. Of course, there are several different models exist. We have a search window right now, which is plus minus 500 seconds for a joint emission. And I know some of you guys asked whether do we get neutrinos? Can we get neutrinos from the kilonova itself? So not just from related to the jet, high energy neutrinos, but some neutrinos which are coming from the ejecta itself, where the kilonova is being formed. So there is a model by Fang and Metzger again. We did a search for that. What we used is actually already the localization of the optical counterpart galaxy. So IceCube has order of a degree or worse localization uncertainty. So we were looking for neutrinos for 2 weeks, and there was no significant neutrino there in that 2-week search. But this is something which is interesting, and there is a possibility, and there exists a model. Yes. This one? Oh, sorry. These are upper limits. It's the upper limit. It's the upper limit. So x-axis is the logarithmic axis in neutrino energy in GeV, and the y-axis is basically a flux upper limit. Yes.
I didn't catch if it's expected to not see any neutrino, or if it's sort of a weird thing that we didn't see any neutrinos from that.
It's more not expected. So is it expected that we would see neutrinos or not see neutrinos? So it's probabilistic. It's plausible to see neutrinos, let me say. So because there are models which allow it. But there are two things. Is the source good enough emitter? And when these neutrinos reach us here on Earth, is our detector in this case big enough to, because neutrinos don't like to interact, right? So they're hard to detect. Our detector is big enough to catch the neutrino itself, which reached us. And the second one is definitely a limitation. So we're really hoping for IceCube Gen 2, which maybe in 10, 15 years may be running. So with a definitely better sensitivity. So predictions, yeah, predictions. Okay. So yes. Yeah. I will talk a bit about that. The search window for gravitational wave and high energy neutrinos. So I will get back to that at that point. Okay. Observational approaches. All right. There are strategies how you search for a counterpart to your gravitational wave event. I mentioned the first one, which we called back then, and we still call it extra strategy, externally triggered search. So we get a trigger, let's say from a GRB satellite, and then flow of trigger, we search in the gravitational wave data. And we either find something or we don't find something. In the second case, we establish an upper limit. We keep doing this, right? There are a lot of like long gamma ray bursts detected, not as many short gamma ray bursts, but we are looking at, and we always analyze the data. We can do a directional search. So we assume the direction of a gravitational wave coming, where gravitational wave is coming from. It's an order of a factor of 2 or so, factor of 2 gain in search sensitivity, what we have there. And it's a bit deeper search, producing upper limits. So, but sometimes an upper limit can be exciting. And this is what happened with the GRBs 07, 02, 01 event. So this was a short gamma ray burst observed from Andromeda. That's very close by, right? So if it was really a short gamma ray burst from a coalescing binary neutron star, actually LIGO would have seen that back in 2007 because it's so close by. And we searched the LIGO data, we didn't see anything. And actually, this led to the confirmation for the discovery of the first extragalactic soft gamma repeater events. So actually, there are these magnetars, very high neutron stars with very high magnetic fields. Sometimes they may have a star quake on it, or who knows what, or some issue with the orientation with the magnetic field when they actually give out a sudden burst, which are fairly short, and their energetics is a bit different. So that was also pointing to that it looks like a soft gamma repeater and a hyperfast, a very large flare from a magnetar, basically. We did not have an extragalactic one until then. That was the first one, and LIGO observation corroborated that as well. So we certainly contributed to that discovery. So in terms of the X-stick strategy, you can always go back to the collected data and analyze. So that's the simplest multi-messenger astronomy search itself. The other one I mentioned, the optical follow-up program. So we search the gravitational wave data, we do the localization, and we give that localization to telescope satellites and other entities, and we point that telescope. So I mentioned that SWOPE will be interesting. Actually, that very first detection from GW 1708-17, which first announcement came from SWOPE itself. So that was very nice. Hey, this is the telescope where our undergraduate students back then went to take data, and we were playing with it. I wasn't, the students were. So, of course, if you want to do this EM follow-on program, you need to do a low latency pipeline because astronomers would love to point that telescope as soon as possible, right? So we were discussing now that how soon it needs to be, and it depends on what you're looking for. So the lowest latency, which we can think of, and I don't have a slide on it, but you can look into it, is called an early warning for a binary neutron star system. So I wasn't necessarily saying, or maybe Jonah looked at GW 1708-17 data and may have shown that it's tens of seconds, actually 30, 60, maybe up to 100 seconds before the merger. The signal is there in the data. So you can start to gain SNR while you're analyzing the data and start pointing, get some ideas. Yes, there is a signal coming in for such a long, for one signal, which is staying in the band for such a long time. And you can do an early localization. It's not gonna be as good as from the merger, but you can probably give an order of 10 seconds early warning. Where it's important, it's just the GRB missions, so they can start slewing.
How was it back then in the one event where we got observation?
No, we did not. It was by coincidence. Okay. No, it was by coincidence. No.
How big is the range of the telescope?
So these GRBs, we see them very far away, actually beyond where. Oh, tiny. Well, it depends. You know, Fermi is very different from Swift. Swift is tiny. Fermi lot actually can see quite a bit of the sky. Fermi GBM much less. It's good to slew. It's good to slew. Swift is incredibly difficult, so they really want to slew. So I actually, with Swift is really the one which is writing this. Okay, it's a personal point of view, not LIGO point of view, because this is a hot research right now in LIGO. I'm not sure that we're gonna see one like that and can point that quickly. We will see. It's more about rates, actually. It's more about rates, so nothing else, because you were asking, or I was mentioning that, yeah, this event was incredibly unique because it was so close by, but we need a really close by event to have that really great early warning. Of course, at the same time, our sensitivity is increasing, so we're getting better earlier signals. So, you know, it's somewhere like between, but it's there, it's working, so we can give that early warning. I don't know how I am doing with time.
Well, right now it's a scheduled coffee break, but if you have a point.
Is it 11 o'clock?
It's 11:05.
Let me finish this section, which is gonna be another 2 minutes, okay? So the search strategy, the third one is the joint search strategy. This is what we use for GWHAN. And there are lots of possibilities here. We are basically combining the data as they come in. You know, LIGO triggers come in, LIGO Virgo triggers come in, or LVK triggers soon come in. And we can connect that trigger to neutrino triggers coming in, okay? And of course, there are two kinds. We have confirmed LIGO events and we have subthreshold LIGO events. And there are high significance neutrinos. If you look at the GCNs, there are these gold and bronze event from IceCube. And then there are subthreshold, everything else. It's basically a subthreshold neutrino, most likely background, but we don't know which is which because a neutrino is just a neutrino. It's not talking to us. Gravitational waves, God, it gives us a waveform. It tells us, we can tell masses, we can tell spins, we certainly tell the direction, but neutrinos also do. They tell us something about the source, unless it's some unknown thing. But neutrinos, there's nothing. Localization, energy, that's it. And the time of the arrival when we observed it. So we don't know anything where it came from, what source it came from. So we have a lot of those neutrinos. We just don't know whether they are really astrophysical or not. And let me go to this one, which puts all this together. You can do this joint search strategy in low latency. And we built an algorithm for that called Llama at Columbia. And we will talk about, not necessarily about Llama, but what's the statistics behind Llama in the next section. Okay. All right, so let's do a break.
Great. Come back around 11:30.
You're welcome.
So if somebody, so I'm gonna lower the standards just in case, I was too strict. If somebody knows how to shoot a picture with this better than I can, then approach me now. Provided you don't go too far away,
You guys online hear me? Thank you. Let's see. Come on, slideshow. All right. We are going to do something more hands-on in the second part. First, we will discuss working with MMA data. We are going to have a little demo, which we played safe, so we recorded it. Actually, Amanda, who is an undergraduate student working with me, and she is online somewhere. I will ask her to say hi to you at one point. We will certainly hear her voice. She recorded the demos since we agreed on what to write, but she wrote it, and it's a very nice demo. And you guys can see how far you can get in a bit more than a year and a half, because she's really getting there with data analysis and using gravitational wave sky maps and so on. So, of course, again, I am saying that we are looking at cases when we have a gravitational wave candidate trigger from the ground-based detector, LIGO, Virgo, and let's look at what's in the MMA data. So usually you probably heard about our detection, but the way the MMA data or the gravitational wave data comes into you, it's coming in low latency. It's coming in as a GCN notice. So there are two ways to come in for the data to come in. One is circular, which has a title, somebody wrote it, and a long text message. You will see at one point an example for that. And it's basically not easy to parse by machine, but the notices are readable easily for you. So that's really wonderful. And what's in the data? Well, of course, what is the important thing? You have a trigger date and time. You have a false alarm rate. you have these things within LIGO. Probability, is this a BNS event? Is this an NSBH event? Is this a BBH event? Is this a mass gap event? We may get rid of that mass gap for the next science run. Mass gap is a mass. One of the masses is between 3 and 5. We were really not expecting such masses. I don't know whether Jonah said anything about that. We can get to that if you're interested and ask a little bit. But the point is, we do see events there, and in some sense interesting. It's there because we just don't know whether, they're likely black holes, obviously, not necessarily neutron stars, and they were historically treated differently in '03. There is this other part, probability, whether this is a terrestrial event. It has to do with the FAR. These two things go together, but you can use all these in a multi-messenger search. So these are telling this one and this one how good an event is. Certainly a false alarm rate is really, we do have a threshold on the false alarm rate. So if it's not looking exciting, you're not getting to see any of that. And very importantly, there is a URL for the SkyMap itself, which is FITS5. Okay, SkyMap actually comes with the distance. It's inside it. And yeah. Did I do that again? I have no idea why it's not reacting to me. I have a feeling I have to do that again. You're right. Okay. Let's do it this way now. I think it's just times out, or it's doing something. Okay, here we are. Okay, so of course we also have data from the offline analysis when we have the run finished, and you have been on Gravitational Wave Open Data Science Center on GWOS website yesterday with Jonah, and you can find each event which we detected, and it has a lot more information. It has a string. I'm sure Jonah showed you how to download that and what to do with that. But there are other things which could be helpful to build an MMA code. For example, there could be certain events you may be interested in. Let's say certain binary black hole events, and notably maybe the high mass ones could be coming from an active galactic nucleus, AGNs, and maybe you want to search for data where the masses are high. So maybe you actually want to use mass as a prior in your search. So you do have that information. You don't get that in near real time. I am for the fact to send this out in near real time. I'm pretty vocal about it in LIGO, but my opinion is not shared. So you may have to wait. I won't promise this is going to come in 04. It's not my decision and beyond my pay grade. But there are also, beyond the strain data, there are also these waveforms in some cases from the burst searches. You can download them and look at them. Maybe it fits some other models if you're interested in. Okay, so these are the data in WASC. And of course, mostly you see results from a compact binary search and all these information. So it's using the model that this system is a compact binary. You're actually looking at the meshed filter search. You're assuming a type of waveform. You're going through your waveform bank and so on, and you get those outputs. There are the burst searches, and it could be very interesting if we have a confirmed event for those unknown unknowns. And in those cases, the online data analysis, because we did send out actually public alert of a burst event, what you get the information is the central frequency and the duration of the event. Okay, if you have, for example, a central frequency order of 1,000 Hertz, oh, maybe this can be supernova because you expect those supernovae being around that. I'm not saying it's necessarily that. Maybe it's a totally unknown thing, and you can come up with your own ideas for that. But that's the point, that these things can happen and exist. I am excited about the unknown unknowns. Maybe they don't exist, but they are unknown, so we will never know unless we really search for that. And one possibility to really discover a new type of source, if that source also have a counterpart. Okay, so we do have matching triggers in the detectors, which look alike in their time frequency evolution. Most likely they are just noise, which just end up just happening right at the same time in both detectors. The detectors are glitchy, they will stay glitchy. This is the life of gravitational wave data itself. If we have more detectors, however, we will be able to have with that. So when Lagrange joins, Cogra joins, I mean, with 5 detectors, oh God, we're going to have a lot less of these glitches coming at the same time. So that will be really useful. And then maybe the confirmation that this is a real event could also come from that. In that case, it's statistics, but there is also, if there is a counterpart and we start to see one counterpart coming at the same time, who knows what messenger? Then we see another one. That's really a hint. So MMA is important for this unknown discovery. It may not happen. We don't know. Okay. So the other messengers also have data, and I am a bit. I am not saying everything what we can say here, but of course, what's coming from the unknown other messengers is the time of the transient. We have a localization of a transient, whether it's a neutrino or whether it's some kind of optical flare. Doesn't matter. You're looking for that. You get your transient event data from whichever telescope, and you can really start looking at what's in there and does it correlate with the gravitational wave event. So at the end, what you're doing, you're comparing the gravitational wave transient information with these other messengers information for spatial and temporal overlap. So spatial overlap is a must-have, right? That source is there. It's right there on the same place in the sky, so there's no way. Now, what's up with the temporal overlap? Well, we have to assume a search time window. And I said I am most interested in the transients, and the smaller the search time window, of course, the easier to make a detection. But of course, you're less likely to find a candidate. It's really a source model dependency. But of course, for example, if you want to show connection, let's say between cosmic rays and another messenger, well, it's a tough call. Mostly because cosmic rays could be charged. They come through the magnetic field everywhere in the universe, and they just come here and arrive at a time which is unrelated to the other messenger observation. Since it's charged, it just comes through different routes, even at pretty high energies. So localization, very high energy cosmic rays, you can start to do point source searches. Those of you who have used maybe Auger data, you've seen that. It's but temporal, it's tough there. Okay. So what else is coming from the other messengers? There could be the energy for neutrinos. That's very important. Higher the energy, most likely it is astrophysical. It's really telling us a lot in the neutrino searches. For optical, we can get light curves. That's very interesting. For the kilonova, we know have expectations how the light curve should look like, and that's certainly a telltale sign for an event. So of course, in 03 we had some additional binary neutron star events. None of them were close, so they're not that close, and they did not have good localization. Everybody searched, they didn't find anything. If there was a kilonova looking light curve, that could have been a telltale sign of that it's a counterpart. It's tough on a large sky map, but light curve would be the helpful thing. So the electromagnetic observations also come in a wide energy regime. And some of them come delayed. We were discussing the afterglow, for example, or sometimes there could be even some periodicity. I will show an example for that. But what is important with all these other messengers, just like with the gravitational wave, it's important you understand your detector. You understand the noise in your detector. You understand the data in the detector itself. So, of course, not just the detector and its data, you also have to have a source model, which connects the observations. Like, for example, I am expecting and searching for a binary neutron star event and its neutrino counterpart. That's a source model. You assume a time window. You assume, for example, does the inclination matter, and so on. Exactly which direction the emission, how it connects to the GRB observations, and so on. And in some cases, observations can guide the source model. I'll show an example here. This is a pretty old one from LIGO. This is still an ongoing search. I'm no longer involved with it. We are looking for actual emission, gravitational wave emission for soft gamma repeaters. This has been ongoing for many years. So a soft gamma repeater, sometimes there are these hyperflares I mentioned in connection to the GRB 070201. There was this one in 2004 in SGR hyperflare, incredibly energetic, and they found this periodicity in this tail. And if you look at the and start to analyze the data in this tail itself, you can actually find it's very slightly here at the top of the screen, showing different frequency regimes where periodic observation was made. This was done by RXT. And these frequency regimes were helping us to basically build a search. Because if there is this periodicity, maybe it's related to a star quake, maybe there could be some gravitational wave emission from there. So we actually were doing fairly narrow band search, but for a fairly long time window. I think these are up to tens of hundreds of seconds. And we were really looking at the data for that time window, and guided by the EM observation and the frequency of the EM observation, and sometimes it's multiples as well. Okay, so that's a possibility. Another thing with SGR, the observation, just a second, was guiding our search was, there was another event, which was this 1900 plus 14 storm. There were multiple observations within a short time scale. It was a storming sub-gamma repeater. It wasn't a hyperflare, but lots of events right after each other. And then the model was that I have a magnetar. It decides to do its own thing. We imagine, let's go starkly, it doesn't matter. But let's imagine it acts like a bell. Each time you hit a bell, it's the same frequency. So what we were doing, we were actually piling up all those events right around the around basically this forest of EM emission, and we were stacking up the gravitational wave signal, and we were doing the search there. These all resulted in upper limits. This is a model. We build a model. We are searching for it and see what we get. This is still ongoing. The Radis magnetar search is still on in LIGO. You had a question. Mm. Okay, I will provide a solution which may happen in the future. Okay. Yeah. So he was asking how can we get the other data from the other observations easily, not just the LIGO Virgo, but there are so many other telescopes, observatories. It's hard to get, and it's a mess. I agree. We were gonna talk about that. Definitely. So let's put everything together. Okay. So my example is the GW plus hand search. So here's the sky map. That's one of the search inputs from the gravitational wave side. And you have to watch out when you're working with the sky map. Is it the one detector sky map? Because that's nothing else but the antenna factor of the detector. Okay, 2 detector sky map and 3 detector sky map. The event actually was right here where that number 1 is. Okay, this is a simulation, but this is where joint gravitational wave high energy neutrino simulated event, we put it in. We just tell the code do this. This is done with base star, the gravitational wave and the neutrino. We put it together and stick it into Llama. But based on this, maybe we would have put the event here. And if we had a neutrino right here, we would have said, oh, no. One detector sky map is not even the 2 detector sky map. It's nice to be on it, but don't expect the highest probability point is the one where your event came from. Okay. We give the distance with the sky map. Amanda's demo will show that. We have the signal to noise ratio or the FAR, or whether is it a terrestrial event and so on from gravitational wave. We have a time for the gravitational wave as well. Neutrino, similar, we have the energy and the position localization uncertainty. Okay. We keep putting it together. Beyond the search inputs, which you are using from the detector data, there are search parameters. We are getting really there to your model, right? Search parameter, of course, this is where you need to know your detector very well. For example, we have background neutrino triggers. I've collected so many neutrinos over the year, millions. They are there. Most of them are background. You understand their background distribution. You really can tell if there is an event, how it looks like at a given point on the side compared to the background. That's important. Similarly, for the gravitational wave, we can create background distributions. We do that with time slides. Did Jonah mention time slides? No. Maximum time difference, let's say, between LIGO Hanford and LIGO Livingston, just based on time of flight, is 10 milliseconds. As soon as you shift your data with more than 10 milliseconds, you can do anything. You create a lot of fake events, basically. You run your coincidence analysis with those time shifted, and you can create a background distribution, okay, of triggers. This is the way we understand the background noise in our data. Okay, and then there are other, like ice cube effective area. Yes? Oh, here, these are the energies. In a second, I'm going there, yeah. And so on, empirical constants. So there are the source parameter. That's the detector first, search parameter, but there are source, okay? This is where your model comes in, okay? Let's say we have a time of an astrophysical event. There is a localization and a distance for that. Actually, distance dependent is very important for certain searches. And it depends on your model, whether, how gravitational waves are emitted versus distance, neutrinos versus distance, and how that changes. But there's also energy. In this case, if you don't know enough, you assume this is the energy distribution, what you expect from the source. So how it emits? What is the distribution of the emitted energies of the neutrino from the given source? It can emit many neutrinos. What is the energy distribution? Very low energy, high energy regime. So that's the plus and minus there. And because we don't know what it does, we just assume let's be as model independent as we can. So you pick something, I want to say trivial, maybe not trivial, log uniform, that's what we picked, because that says that if an event is more energetic, you're less likely. So it's harder to create a high energy neutrino. That's the point than a lower neutrino energy neutrino. So log uniform can work. So. Of course, you can have other models. It's up to you. It's the work of the theorists to figure that out. I am a data analyst. I am happy to put in another model if you provide me something good. Until then, we have log uniform for now. Time window. I mentioned it's very important. For the GW hand search, we are using a plus minus 500 second time window. We wrote a paper on this back when we were formulating the search, and this is actually coming from studying gamma ray bursts and its precursors. So assumption was gamma ray bursts, we expect neutrinos, high energy neutrinos from gamma ray bursts. Unfortunately, we haven't seen that yet. It doesn't mean that that's not the case. It's just not that good of an emitter, and we are not as good at detecting them because neutrinos just don't interact so well. But looking at gamma ray burst and assuming a precursor activity and looking at how many precursors, the statistical data about GRB precursors, we learned that we can have a central engine which is active around the precursor time. When you see the precursor from gamma, of course, the jet broke out. That's why you see the gamma. That's around this time scale. And then this is the major GRB. Again, jet broke out. And before that, there is probably some activity in the central engine when both gravitational waves and high energy neutrinos can come. So if you start to add this up, we can have a search window of plus minus 500 seconds. Okay. Now comes putting this all together. We have source parameters, right? We have search parameters. We have the data itself. What do we do with that? Well, we form some hypotheses because we're asking if we see a coincidence, spatial and temporal coincidence, is this real or not? So these are the hypotheses, a signal hypothesis. So both the gravitational wave and the neutrino came from the same source, okay? There is the null hypothesis, they are both background. And there is the chance coincidence hypothesis that only the gravitational wave or the neutrino signal is, one of them is background and the other is not, okay? That's the chance coincidence. The probability for that, especially with neutrinos, in our case, we have 6.4 neutrinos on the sky on average in our IceCube search. So that's the 1,000 second time window plus minus 500 seconds, total 1,000 seconds. And we know what's the neutrino rate with which we are detecting. It's 6.4 on average. So the chance coincidence is very high. We really need to understand that before we can really evaluate the significance of an event. There is a negligible contribution that both signals came, but they're not connected. Came more or less same localization around the same time, but they're not connected to the same source. Well, we don't deal with that. That's very negligible. So what we really want to find is that evaluate the significance of our event is basically using base factor, or we call it odds ratio statistics. So what's the probability that the signal, which we think is a signal, so this coincident event candidate, is really a signal, given that we have all these parameters which were discussed. And then we also want to evaluate that and compare that. So take this ratio that is actually a noise, given that all those parameters which we were discussing. So we find these odds ratios, and to find these parts, we use Bayes rules. You can go and open your statistics books. So I'm not going to go that. We discuss Bayes rule because we run out of time. But basically, we use this odds ratio as test statistics, okay? So we are running our analysis code, Gaussian times, on created simulated events, and we create a background distribution of these events. And if we have a candidate event, we compare to this background distribution. Okay, so this is the mindset behind the analysis itself. So we are putting it together still. And now this is a lot of equations and so on in terms of how our analysis works. But we had the inputs, we find whether we calculate basically the background rate based on those simulations that I mentioned. We calculate for a given event, which we observe the chance coincidence. And of course, we can also find the same thing for a signal hypothesis. We start to put together, we apply Bayes rules over and over for finding all those probabilities, and we can find the odds ratio in each case. So we run this for the background, we run it for a real event. We were asked by IceCube to evaluate the double neutrino case as well, when two neutrinos came at the same time. It's very, very unlikely, but that's why you see the two neutrino there. It says that. It's written down in this paper by Bartosz et al. Okay, it's heavy reading for somebody who didn't have statistics first. It's getting there if your background is, it's a fun reading otherwise, but you know, if you want to get into this business of finding MME events, statistics is must have, so just go through it. Okay, what else do we need putting it all together? Well, we need a pipeline, okay? Because there's one thing I described how we do it, but because we have to do all this background distribution, you need to have a pipeline which can do all these tens of hundreds of thousands of background runs, and of course can run extremely fast because you want to send out the low latency alert on GW plus hand events to an astronomy telescope. Look in the sky, because that tiny 1 or 2 degree neutrino localization is so much smaller than the LIGO sky map. So search there first, prioritize that point. You have a question? Algorithm for multi-messenger astrophysics. We call it LAMA. It's our acronym for that. So pipeline, all these. This part is LIGO Virgo, okay? So LIGO and Virgo finds its own events, creates a sky map, tells us significant and so on. And at one point, it passes to us. So LAMA is here. We have a trigger listener right now. This is the point where I would love to have this part replaced by something else, this plumbing, because this is difficult to upkeep. Of course, we get the things from IceCube as well. We are under construction. We can get, hopefully in the long run, events from GRB and build it into the statistics. So here we actually do the statistics work, which I described in the previous slide, and say, is this a significant event? Basically, this is finding a p-value for O3. We were using 1% p-value to send out alerts. So we sent out, I think, 3 alerts during O3. And astronomers unfortunately didn't find anything. What I am going to show you an example where something was more or less interesting at the end. Probably wasn't, but still, we had an exciting half a day. That's what it is. So this is more about the speed. So we are waiting 500 seconds to collect the last neutrinos because we have a plus 500 second window. And of course, at the end, we have minutes of runtime to get the neutrino data and get the p-value and send it out. Yes? Yeah. Because I am associated with IceCube. IceCube has the highest rate right now. We are also working with Antares. Our offline searches always use Antares data as well. We are actually doing O3 offline search with Antares data as well. And there is a possibility to do more, but of course, more detectors, more to understand. But yeah, obviously, it's interesting to do it with the other detectors. So here's the background distribution example. This was actually for O2 when we were testing and actually we published an analysis on these events as well. All right, so here we are. And this is all of it, putting it together. So if we don't find anything, we set an upper limit. The papers on the right describe the pipeline on many different ways and its different versions and so on, and the statistics. I'm gonna go to the next slide because I said GW plus hand event, but what if we get lucky? Okay, because I said, all right, we can tell whether the GW plus hand event is significant enough. We do this, we are combining the events this way, we run it on Llama. But what if we have another observation? So what happened for this one trigger, 1912, 16 AP, this was actually a BBH. We sent a neutrino location out. So we tell the astronomers, look right there, which is the neutrino location. So this is fairly small compared to the rest of the gravitational data, and we asked them to look right there. And Hawk came back with, oh, that's quite interesting. I am finding something right there within the joint localization area, but of course, where they found something was a bit off from our 90% probability. So that's where the whole day got less exciting. But still, it actually even triggered an additional analysis in radio as well. So this is like 4 observations after each other. But what if we find something there? How can we tell that they are really related? Well, here's an example going beyond 2 messengers. We actually put together a paper with Doa Veske, who's a graduate student at Columbia, and which would be a general treatment for multi-messenger search. Okay, so if you have n messengers, so not 2, not even 3, n messengers, you can actually derive that how many hypotheses are. But let's go for 3 messengers, and one which may be a promising one. I hope we may have at one point such a detection. We may have to wait for IceCube Gen 2, but shall see, or KM3net, or since you're asking for other detectors, which will be coming also. These are the hypotheses. There are 8 of them. Okay, so same source, and it's a signal GW hand plus GRB. Everything is coming from the same source. Signal hypothesis 1. But you know, if any 2 of them are joined and the other one isn't, it's still a signal. It's still an MME signal, just the third messenger is not connected. And then, of course, we can have that only one of them is a signal into your background. And then, of course, we can have basically the null hypothesis. All of them are backgrounds for this joint source. So you really have to derive all this and put it all together. We actually we wrote down this situation in that paper with Veske et al. And for the GW neutrino and GRB case, these would be the input. And for, of course, for the GRB would have the sky position, angular uncertainty. We may actually get it as a Fitzfile map. Time and duration, significance, and influence from the GRB could be your input parameters. So at the moment, this is not coded into Llama. We are still working on putting all these simulated events together and do the coding itself. But the treatment is there, and doing this model, and there is no other way. But you have to assume a model. By the way, that's also written down in the paper. You have to assume a model. So, of course, at the end, your search is as good as your model is. As soon as you have priors, you're getting a result which describes your prior. Okay, so multiple coincidences are inevitable. Okay, we're going to have these. And to do this statistical inference is basically a requirement from now on. Gravitational wave detectors sensitivity is increasing. We're going to have more events. This chance will happen that we're going to have 3 things happening, and we will have to tell what it means. So that is the thing for which we have some solution. So what I'm gonna do now is I'm gonna ask Amanda whether you are on, and just to say hi to everybody because she has a demo. And how are we doing with time?
We should probably end around 12:40. That would be an hour.
So that
That's-
time is not good,
It's
right?
about 5 minutes late. It's 12:17 right now.
Okay. All right, Amanda, do you hear me?
Yeah, I can hear you. Hi, everyone.
Hi, everybody. So we are gonna upload so we have around 15 minutes.
15, 20, yeah.
Okay, there are 3 demos by Amanda. First one is a joint localization demo, which runs for 14 minutes. Then there is a demo on using SEMA. And there is a demo on doing joint sky localization between actually a neutrino event and an AGN catalog as well. It's on her GitHub, so you can all download and look at it. Now, I have a feeling that I'm going to have to talk about the least exciting one in some sense, but please look at the other demos, okay? Yeah. So it's in my, Amanda, can you send the link to your GitHub?
Yeah, of course.
Okay, so you remember where the SEMA demo starts?
I think it's the third one, so it's right at the end.
You know what? I'm going to talk a little bit about SEMA. We won't do the SEMA demo. We will do the first demo, but I'm going to say a bit about SEMA before we do the first demo, okay? I think that's what we are going to do, okay, Amanda? So we do a joint localization demo, which is actually GW 170817. And if you can get it ready, maybe you will play it. Is that easier? In the meantime,
Okay, yeah. Sounds good.
while that's happening, I tell you about SEMA. Because there was this question, and I said I will say something, and you asked, right? What's the solution? I'm not saying this will be the solution because we are sort of in between funding cycles, but I'm really hoping this is one of the solutions. So NSF funded a project, there are like 9 or 10 institutions involved in it, called SEMA Cyber Infrastructure for Scalable Cyber Infrastructure for MMA. And SEMA, this is our, hey, this is here. This is our website, SEMA.org, you can find it. And basically, this was a conceptualization project, and now we are in the first prototyping project to produce an infrastructure where multi-messenger astrophysics data can come in. So let me go here. Actually, this is it. This is from Andy Howell, who is on SEO, Las Cumbres in Chile. And how did GW 1708 17 happen? They got an alert from GCN. Hey guys, this is a BNS signal. It's awesome. Then came the panic. What do we do? Then they started to look at, how are we gonna do this localization information? Because it's too big of a sky map. And then others were also searching, and we are competing and so on. So they backplayed, so on, form collaborations sort of quickly because everybody wants to find it, but they realized that even though it was a small sky map in LIGO standard, it was still big for those telescopes with their field of view. And some work together, some didn't, but it was many hours by the time actually their observation went out. Like it was definitely next day. The event happened around 13 something UTC, and it was the next day early morning when the observation came out. So there was no discussion. I'm gonna search this part of the, or you had to form it just like that. Okay, you even had to download maybe your catalog at that point if you were not ready. So what do we do? So we would like to avoid that. And we realized there are key ingredients which are needed for such an infrastructure. And that's what CIMA is hoping to solve. So the vision is that we will receive an alert. You will receive an alert as an astronomer. This is a very much an astronomer point of view. So I'm using Mario Urich's slide. He is in LSST. Okay, so LIGO, Ice Cube, and LSST are key stakeholders in CIMA. These three collaborations have significant members within CIMA. Okay, so you receive an alert. You're hoping that your telescope will automatically observe. It gets the alert. CIMA does something, sends you. Look there, okay? And then the data could be even automatically reduced and instantly made available to your collaboration. So you can form internet collaboration, you can set up who you are working, whom you are working with, but within those people, if you form your own collaboration earlier, you can share your data. You can decide who is doing even automatically which part of the sky, because for example, you know, there's a telescope in Australia, there's a telescope in Chile, and so you're gonna have to, it's kind of maybe too big, you can certainly divide who has the good weather right now, who may have a better weather later on which part of the sky. And then, of course, machines and humans make inferences based on the data. And I'm gonna go here. So what are we building in CIMA? We are building a pub subsystem, publish and subscribe. We call it hopscotch. And basically every detector sends in its event to hopscotch, but it can also pull event from the others. But of course, we all have collaborations and data rights, right? We have the subthreshold searches within LIGO, like the LIGO Virgo subthreshold search, where we are using subthreshold data, is a memorandum of understanding based search. So we agreed to share the data between each other, but not with others. So we don't want it to be public. So it's very important that we respect these data rights, and we can enable collaborations like that. So for that, actually, we do have an identity and access management system. So beyond HOP, this is the other key ingredient, because the astronomy sociology is not working that everything will be fully public. Certainly not yet, and it's not going into that direction still, but a memorandum of understanding based collaborations and an easy way to support that through CIMA's access management system will be a key part here. We are planning to have archives, data lakes. So we are going to store events. You can always go back to those old events. So you can even put your catalogs there if they fit, okay? Data lake is incredibly important because this allows you cross-matching, localization, either catalogs, go back to an old event, maybe that's related somewhere or another to a new one, and so on. Okay, search the sky, what happened within CIMA, right in that position earlier on, back in time onto CIMA's data. And another thing which we are building, this is important for Llama, we're building a science platform, science analysis platform. So you can pull your events, you can create basically your plumbing for your pipeline right on CIMA and just do your statistical run on this analysis platform. You're creating it. It's a platform to create your environment, your own code, your own search within the CIMA archive and incoming low latency events based on, of course, your data rights after you log. Okay, so this is what CIMA is. I hope it will be funded and it will revolutionize it. If it's not going to get funded, I don't want 04 run like 03 was, but then that's what's going to happen. There will not be a big change, but this is really, really needed. Okay, I'm gonna stop here. And Amanda, if you have your demo and I stop sharing, and let's start with the first 14 minutes or so.
Okay, no problem. I can share my screen with you guys. Can you hear that? Just checking.
Yeah.
Okay, awesome.
Do you hear her?
We can hear her talk, but we can't hear the audio.
Oh, okay, okay. Stop share, Amanda. Maybe let me, oh, okay, Amanda, I found the video. I thought I had it open. If I am gonna start sharing this. Apologies. Wait a second. Let me try it myself, and then we go from there. Okay, just a second. Is this not working? Okay, Amanda. This is should I connect my
I think you have to share the audio.
on Zoom?
Yeah, take it over. Why don't we have
Oh, I know what's happening. If I no, that's not.
no, I think you have to share audio through Zoom from your
Okay.
mute.
Oh God, there's no easy way of these things.
Okay, sharing audio my computer. So
So we go there and it was just you go.
okay, so which one?
Okay, actually, it's gonna be here. I just open it
So
again.
all you have to do is like check this button,
Okay.
so it will also be with sound.
Okay, sure. But it's there now.
Hi everyone, my name is Amanda and I'm going to be presenting to you 3 demos that are for people that are starting off at multi-messenger astrophysics and people that are interested in knowing a few of the specific techniques that we use for data analysis and visualization in multi-messenger astrophysics. So this is supposed to be an educational resource. If you have any questions, please feel free to email me or to even add them to the Git repository that I will give to you at the end of this. So we're going to start off with the GW 170817, GRB 170817, and IceCube neutrino localization demo. So just a few definitions of names and acronyms. GW means gravitational wave, as you probably know. GRB means gamma ray burst. And IceCube neutrino just means neutrino. So at first, what you can see here is an index to help you navigate through the site.
Okay, I have no idea what's happening.
Yeah, so I think only share the screen that you're playing on and then share sound. I mean, Amanda can also do it. But it's just that when she shares, she has to also click share computer audio. correct? So Amanda, can you hear us?
Yeah, I can hear you.
So can you try and share the video again, but just try to click the box that says share computer audio as well.
Yeah, sure.
Let's try that.
Resource. If you have any questions, please feel. Does that work?
Yeah.
Awesome. Okay, great. Hi everyone, my name is Amanda, and I'm going to be presenting to you 3 demos that are for people that are starting off at multi-messenger astrophysics and people that are interested in knowing a few of the specific techniques that we use for data analysis and visualization in multi-messenger astrophysics. So this is supposed to be an educational resource. If you have any questions, please feel free to email me or to even add them to the Git repository that I will give to you at the end of this. So we're going to start off with the GW 170817, GRB 170817, and IceCube neutrino localization demo. So just a few definitions of names and acronyms. GW means gravitational wave, as you probably know. GRB means gamma ray burst. And IceCube neutrino just means neutrino. So at first, what you can see here is an index to help you navigate through the sections of this demo easily. Then next, we're going through imports. These are just general imports that you will need to run this demo. This is actually pretty interesting for people that are starting off and maybe thinking of making their own Git repository for different projects and stuff like that. So I'm using sys. And basically what sys is doing is I created this functions Python file, which has all of these big functions that I didn't want to have in the demo. And then I'm just using sys to import functions from that will be available. That functions file will be available in the Git repository if you're interested in looking at it. Specifically for these demos, I am importing the plot mole view function. So this plot mole view function, I altered it a little bit for the purposes of this demo, but it was originally written by Steph Countryman, a previous PhD student with Zsuzsa. So yeah, so first of all, we are importing gravitational wave data for the BNS merger, or the binary neutron star merger, GW 170817. And you can find that data in the GW 170817 data release. And the link can be found down below in resources. So just a quick mention of how to get this demo to work if you are going to be running it by yourself. I put a data, a file directory called data in the Git repository. When you download all of that data that you're going to need for these demos, you just put it in there and everything should work fine. So first of all, I'm opening this just using Astropy tables. So Astropy tables is a lot like pandas. If you know how to work with pandas, then you probably know how to work with table. Basically, almost everything you can do with pandas, you can also do with table, and you can go between the 2 data frames as well. Astropy documentation will be linked down below if you want to take a closer look at that. So the first thing I'm doing with this is I'm adding an index column because the indexing scheme for this data is actually not explicit. And I would like to know which pixels I'm dealing with. And when I say pixel, it means that I'm dealing with a HealPy localization sky map. HealPy documentation will also be linked down below. So basically what this means is that I have a sky map, and this sky map is organized in pixels. Each of those pixels have different density or probability density indexes. And then I can plot that and see the areas that are denser or that have more probability in the sky, basically. So we're going to go through more about HealPy and HealPy maps, but that's what I mean when I say pixels. So this index column that I'm adding is serving the purpose to prevent pixel scrambling, or when I'm dealing with the data, I'm just preventing the data from becoming scrambled so that I can correctly plot it later and know which pixel I'm dealing with each time that I query the data. So this is a little table that will show you a little bit of what is in that data. So this is LIGO data for single order sky maps. So here you have the index column that I added, and then you have the probability column, which is the probability of each pixel. And then you have dismu. So dismu is just the LIGO's estimated distance for that event from us. So from us, at what point that event actually happened in the sky. And then dis sigma is the error on that distance. And dis norm is a normalization factor for the distance. This is used for statistical purposes. We're not going to be using this in this demo. So next, I want to make a quick mention to multi-order sky maps, which are another type of pixel scheme that you can find for sky maps. So for each of the events, you can pretty much find single order and multi-order sky maps. The only difference between them is that for multi-order sky maps, instead of just having one pixel size throughout the entire sky map, where you have lower probability or lower density, you will have larger pixels. And then when you have higher probability or higher density, you're going to have smaller pixels or higher resolution. So and you can go between the two. So you can go from a multi-order sky map to a single order sky map by using this LIGO.skymap.mock.rasterize function. And the link to the LIGO mock documentation can also be found in resources down below. So next, I'm going through the FITS header. So this file is a FITS file. And when you have a FITS file, you can go through the FITS header. And the FITS header has a lot of information about the file and also the event. Some of it is very important for us. So over here, you can see the length of this data. It's 12 million pixels. So that's a really big data set. And then over here, you can see all of the columns that are in the data set and also the units that they're in. Then you can see the pixel type. So this is HealPix or HealPix pixelization. It's just HealPi pixel scheme. You can see the ordering, which is listed as nested. So the ordering can be either one of three. So if it's a multi-order sky map, it's going to be a Munich ordering scheme for the pixels. If it's a single order sky map, then it can either be single or nested ordering. So nested ordering means that it will start at a point for the first pixel index, and then it will go around it and then stop at some point, jump to another point and do the same, go around it. That's why it's nested. It's a little nests all over the sky map. Ring ordering, basically, you're starting at the top of the sky map and then you're going around it like that, and that's just ring ordering. So this is really, really important if you are plotting things or if you're cross-matching things to know this. Otherwise, you're going to be scrambling your sky map and things are going to be all over the place if you get the ordering wrong. And that can really mess up your cross-matching or your localization. So the next thing is also incredibly important for localization and cross-matching, which is the coordinate system. So this particular sky map is in celestial coordinate systems. There are three coordinate systems in astronomy. They're either ecliptic, which is basically your field of view, you know, what you can see in the horizon up, and then that's your coordinate system. And then you can also have galactic. So the galactic coordinate system has 0 Ariandak right at the center of it. So that's the galaxy kind of point of view of coordinate systems. And then celestial coordinate systems, or equatorial, is basically the Earth's coordinate system projected onto the sky. So the equatorial line is going to be the 0 line for declinations. And you're going to get the point of view of Earth. So Earth as the center, and then this sphere around it as your coordinate system. Again, very, very important. If you mess these up, you could mess your localization, you could mess up your plotting. So very important to keep these straight throughout all of your data sets and throughout your plotting. So the next thing that you can see here is the N side. So the N side is the resolution of the HealPi sky map. So the higher the N side, the smaller the pixels, and the higher the resolution that you have. Basically. And when you have a multi-order sky map, you're going to have various different end sides throughout the sky map. So here, I mentioned this before, this is index scheme. So it says here it's implicit. What we made before was make it explicit so that we don't scramble the pixels again. So this is the event GW 170817. And then these are the date of the observations. So the first here is an UTC date time. So this is just regular time that we know and is pretty familiar to all of us. The next one is MJD, or modified Julian date. So this is the Julian date from a day in the 1980s, and then it's just counting the days from that date. And this is actually very interesting for us because, as you can see, it's a float, or a single number, and then you can do things with this number when you're working with computers and stuff like that. So it's useful for us to have that there. And then you have some more information about the sky map, the event, and the file that it's in. So the next thing that we're going to do is we're going through the highest probability pixel, and we're going to find it within the data. So here what I'm doing is I'm querying the data, finding the highest probability pixel, and then I'm using this HealPy function called pix2ang, and I'm getting the RA index for that pixel. So this is what you can see here. Remember, all of the documentation for HealPy is linked down below if you want to take a look at that. Next thing I'm doing is I'm plotting the BNS, the binary neutron star merger sky map. So this is the sky map. Again, remember, I'm using the plot mole view function. For the specific purpose of this demo, it's going to be in the Git repository. But if you are using regular plotting functions from matplotlib or from HealPy, it's not going to look exactly like this, although it will look very similar. So this is a close-up. You can see here, if you look really closely, you can see the pixels, and this is the highest probability area of that sky map and the localization of that event. So the next thing we're doing is we're going through Fermi GRB 170817A data. So again, the data link is down in the resources. You can download it from there. So this data set is a little bit different from the previous one. It is a list of RA's index for the contours of this data set. So basically what that means is you have a 1 sigma, 2 sigma, 3 sigma contours of the error of the localization of that event, and then you can plot that on top of a sky map and see if it overlaps with the localization of the sky map for GW 170817 as an example. So we already know that it does overlap because these events are correlated to each other. So here I'm just plotting that event. As you can see here, this is the sky map for the GW signal, and then the 1 sigma, 2 sigma, 3 sigma confidence intervals for the contours of the GRB signal. Again, GRB gamma ray burst. So this next part is we're going to ask, is there a coincident neutrino in this for these events? Or is there a neutrino in the IceCube data set that we can find that might be correlated to that event? So spoiler alert, the answer is no, this has already been done. So 170817 means that it occurred in August of 2017. So we already know that it's not there, but it is a nice exercise to do this anyway. So again, the link to IceCube data releases can be found in resources. So here is just a glimpse into IceCube data. Again, here you can see the date here is in MJD. So this is important for us to find the closest neutrinos to that event. And that's exactly what we're doing in this part over here. So I'm looking at the BNS MJD date, and then I'm looking for closest neutrinos within plus or minus 500 seconds of that event time. And I found 4, as you can see here. So the final localization sky map that you can see here is plotted with the localization sky map for the GW event, the GRB contours, and then also the 4 neutrinos plotted on top for their RA's index. And here, as you can see, these are just the resources for this data. So next up.
All right. So, sorry. It's okay. So this is where we are going to stop because I know we are running out of time. There are 2 more demos. So this is really just to get started, to plot anything you can think of, basically. Fitz maps from LIGO, which is very difficult. For the GRB data, there are sometimes Fitz map files available. You can pull it in and work with that. If it's contour, then you have an example. For IceCube, the IceCube data, unless it's a large offline analysis data release, which she used, the real time is not. So that's the only thing which is openly available. So this is the latest data release, which ended in 2018. I don't know which, probably May is the last. Usually it goes the cycle with May. So that's another thing which is available. This is for fun to do your own things. The second demo is showing a cross-matching example between a LIGO sky map. We picked GW 1905-21, which was the highest mass BBH event for which there was a candidate. It's not, we don't know, it's just plausibly related. It's a candidate ZTF event. And it's coinciding the ZTF event was chosen, well, to look for this in the sky, that we were looking for AGNs. Okay, so this cross matching is done with an AGN catalog. The real, analysis itself, or what was driving the astronomer search, was a bit more pre-selection of the AGN catalog itself based on some other things in there. But right now, Amanda's demo is just cross-match a galaxy catalog with sky maps. So that's a useful example. There are, I don't know, 100,000, I don't know how many, a lot of AGNs within the sky map is large as well. So it's not useful for anything, but it was useful. It's useful for you to use it as an example. And the third one is a demo of hopscotch itself. So the CIMA product as it stands. Right now, we don't have the GCN notices, which is the machine readable, running into hopscotch in its public version. So the demo is showing GCN, reading a GCN circular and then just doing some manipulations, looking for basically text-based search on that, and then doing some other cross-matching work. It's more like this is what's coming, but more, it's going to be a lot more than what you see on the demo. It's just a first introductory example. And I think this is where we need to stop because we ran out of time. And let me thank Amanda, and I want to look up the screen, but she's not there. So Amanda, thank you so much. I see you on my screen, on my Zoom, and I really appreciate you joining and certainly preparing 3 demos, which are available. And I think she sent on the chat window the link to her Git page. And please look at them and use it. We are very happy if you, this may be your first introduction to MMA, using MMA data itself and combining events from different detectors. Thank you so much. Sorry for the overtime.
Yeah, so if there are further questions, put them on the slide.
Yeah, one more thing. Further questions, please put them on Slack. But I will not answer this week, just next week. Okay. I just want to let you know, don't expect that I will answer, but I will look at it next week and I will try to answer every question. Unless Amanda will be able to answer some of them, she may. So thank you so much.
So we're going to try to keep on time and come back to 1:30 because our next speaker is joining us very soon. So fortunately, it's a little bit of a short talk. Sorry.